This lecture aims to explain the main terms of the building's energy balance. A building, considered as a thermodynamic system, is an open system whose boundary, the envelope, separates internal phenomena from external phenomena and is crossed by fluxes of energy and matter. These fluxes vary over the time. Therefore, the building is a dynamic system not just because the light illuminates it in a different way depending on the location, season and time, but also because there is not a single molecule of its structure that does not continuously change the thermodynamic parameters that affect comfort and energy demand. If we imagine a bucket with holes in the bottom and in the sides, we know that if we fill it with water and we want to maintain a certain level, we need to provide as much water as it loses. Likewise, to maintain a certain temperature inside the building in a cool period, since there are heat losses, we must provide as much heat as it loses, and this is done with the heating system. The holes of a building in winter are the transmission heat losses through the envelope and those due to air infiltration and ventilation. Actually, there are not only losses in the relationship between the building and the environment, there are also solar gains, as if the bucket was placed outside, where the rain helps to fill it. To these gains, the internal gains, which are the heat produced by the occupants, lights and equipment, must be added. In summer, things go in a similar but opposite way, as in a boat with leaks in the hull. To keep the boat floating, water must be pumped out. This corresponds to the building in the summer, when the heat penetrates and you have to pull it out with air conditioning. The penetration takes place through walls, roof and windows, and through infiltration and ventilation. In this case, there are also solar gains, but they now do not help. On the contrary, they tend to increase the temperature of the environment, in the same way that rain would fill the boat faster, raising the water level. The sensible energy balance of a building at time tau, expressed in watt, can be solved according to this equation, where Q tau is the heat flux which flows through the roof, each wall and the floor. QGL tau are the heat gains through the windows. QV tau is the ventilation heat flow. Qi tau are the internal heat gains due to people, domestic appliances and equipment. Qm tau is the sensible heat demand compensated by the heating or cooling system. Thus, in general, the energy balance of a building envelope regards the thermal energy flows required to maintain the desired condition of temperature and humidity in rooms. The architectural choices are crucial for the part of the balance that covers the sensible heat, which is that correlated to a temperature variation. The balance of the latent heat, which instead is that released or absorbed when the water, contained for example in the air, changes state, depends only on the internal sources, people, plants and kitchen, and on outdoor air conditions. Thus, the envelope characteristics have no influence on it. To better understand the thermodynamic processes involving sensible and latent heat, the psychrometric diagram can be used to represent the most air properties through a data pair, which can be, in example, the dry bulb temperature and the humidity ratio, the dry bulb temperature and the relative humidity, the dry bulb and the wet bulb temperatures. Given a pair of these values, it is possible to read all the others. Therefore, a point marked in the diagram represents the condition of the air at a given place and time. For example, if we cool the outdoor air initially at 32 degrees Celsius and 60% of relative humidity and bring it down to 26 degrees Celsius, the resulting process in the psychrometric diagram is represented in the figure. The process is called sensible cooling and is associated with an increase of relative humidity. To cool the air maintaining the same relative humidity value, water vapor must be subtracted from the air, as indicated in the figure, in which about 5 grams of water per kilogram of dry air are condensed. The process is called sensible cooling and dehumidification. The sensible cooling and the humidification transformation actually occurring in air conditioning system is the one indicated in the figure. It involves the cooling of air to reach the saturation curve and moving along it to the point where the required amount of vapor is condensed to achieve the desired relative humidity. Finally, the air is heated at the final set point temperature. The total heat required to perform sensible cooling and the humidification is called enthalpy, which is equal to the energy that has to be supplied for each kilogram of treated air. By analyzing the psychrometric diagram, it can be seen that in air conditioning, the subtraction of latent heat, which corresponds to the condensation of the water vapor, requires more energy than subtraction of sensible heat, which is related to the temperature decrease. In conclusion, the total energy balance of a building has to take in consideration both sensible heat fluxes, which are mainly related to architectural choices, and latent heat fluxes associated to humidification and the humidification processes.